All right, I'm going to start doing number 10 today. And then what I want to do this class is just put a couple of these kind of problems up. And you can find space on the board in small groups of people. And I just want to see you work through some of these problems. Hopefully we can get some of the issues ironed out. The people who are understanding stuff can sort of explain stuff to the other people and whatever. I just sort of want to see on the board where everybody's at right now. Okay, so number 10. These are rigid bodies. Oh, and the test, I'll try to have those back Tuesday. I don't have them done yet. And I owe you a ton of homework and stuff, and I'll get that back sometime as soon as I can. I was counting on getting a ton of stuff graded on Tuesday, and then you might have noticed there was a little boy sitting under my desk while you were taking your test. My kid was sick. We couldn't find anyone to take care of him, so that kept me from getting anything done. Okay, rigid bodies, number 10. So that problem looks like this. You have a downward force of 140 pounds. You have a cable there connected to the wall. And you have one cable going through these pulleys. To there. And to there. And then there are a million dimensions. So these are in a vertical line. Doesn't really look like it. These are all in a horizontal line. This distance is 120 inches. This distance is 44.8 inches. This horizontal distance is 100 inches. The other horizontal distance is 136. This 120 is wrong. That should be 72. And then the 120 goes to here. And then it's 140 all the way to the end. Thanks. Okay. And I think that is, one more thing. These are each, so this is 10 inches. And this is 10 inches. And that defines the problem. The mass of the structure itself is negligible compared to the other forces is the idea, so it's not included. It looks like that's all the time we have in class today, but those are the dimensions. I hope that helps. Not really, but that did take a long time. Thank you. I'll be here all week. So I think the easiest way to approach this is to first, and let me add the coordinate system. They give a coordinate system, so you don't have to think about it really, but the most sensible coordinate system is the one that they give you. It has the x-axis pointing straight out of the beam, the y-axis pointing up, and the z-axis pointing this way. And the nice thing about that choice of coordinate system and that choice of origin is that origin is at the best place for the about point too. So we don't have to think about, translating stuff too much. When the origin and the about point are at the same place, the row vector is the coordinates for where every force is applied, So in this problem, and probably generally in problems like this, I think the most sensible first step is to just come up with the coordinates of all these points. So let me give the names of these points. They call the end here A, the intersection here B, this pulley C, and then D is back at the origin. And then on that cross piece, this is E and F. And then the cable connections are G, H, and I. And so we're just going to go through and give the coordinates of each one of those points. So first, point A, that is, so starting at the origin, that's just going 140 inches in the positive x direction. So I'm going to write that as 140, 0. You could convert this to meters, but we could just as well do it with forces of pounds, length units of inches, and then torques, moments are going to be in inch pounds. The point B is going from the origin to here is 120 inches. In the positive x direction. And then C is just 7200. Any questions about any of those? Well, D is the origin. So those are all the points that are just straight along the x-axis. And then E is, so to get from the origin to E, you have to go this way 120 inches along the positive x. And then you have to go in the positive z 10 inches. So E is 120, 0, 10. F is 120, 0, negative 10, because once you get to that point B, you just take the negative z direction 10 inches. And then G, from the origin, you just follow the positive z-axis 136 inches. So that's 0, 0, 136. H, you go from the origin 100 inches in the negative z direction, 0, 0, negative 100. And I, you go from the origin in the positive y direction, 44.8. So 0, 44.8, 0. And now I'm going to draw the free body diagram. So let's say we're isolating this. And you have a couple of options here about what to isolate. I'll talk about that in a second. We know we have a downward force of 140. And so now we're just looking for contact forces. Back here at origin at point D, that's a ball and socket joint. So we have a force vector. I'll call that RD. And now we just have cable forces. At the pulley here, this is the point C. We have a force like this. And now, this can be confusing, but you need to just think carefully, like you're going around the boundary looking for contact between your body, the boundary of your body, and things that are not included in the body. Well, right here on this side of the pulley, that cable is touching the pulley, right? And so we need to have another force, T, like that. Okay? And now keep going around, and you get to here, and the that same cable is touching this pulley, and it's going back towards the other one, like that. And then you get to the other side of that pulley, and there's another force, P, like that. And then nothing else is touching as you keep going around. You get here, and there's one more cable. That cable isn't the same one as this one. These are all, the magnitude of those forces is T because that's all the same cable. So you get over here and you have a different one. I'll call that T2. Now, right now, we're going to have to, so this is fine. And if you do all this right, you'll get the right answer. But one thing that you'll see if you do it like this is this force and this force, they're equal and opposite. They have the same line of action, right? which means it's an equipolant system to take either one of these forces and move it to where the other one is. You know what I mean? And so like if you took this force and moved it to here, those forces cancel each other out. They don't produce a moment. And so there's another way you could draw this free body diagram where you just wouldn't, those forces wouldn't appear. And that would be like, include that little piece of the cable in your isolated body. Then you have this force RD, T there, T there. These now, two T forces on the other side of the pulley are now internal loads, and so they don't show up. 140, T2. Okay. The difference is that in this one, the isolated body didn't include any of the cable. And so I had to, in my free body diagram, apply a cable force going this way from the pulley, and on this pulley, a cable force going that way. On the second one, the body I isolated included a piece of that cable that went between those two pulleys. And so since the force of that pulley, so the force of the cable on that pulley is part of the isolated body acting on another part of the isolated body, those two forces disappear. It's just, it lets, if you see that, it lets you save a little of the math, you know. If you don't see it, you do a couple more lines of math and you get the same answer. So it's not like an urgent thing. Okay, so now rho, force, moment. And our about point is going to be the origin. That's where we have the most unknown forces. Okay, so first of all, this force RD, what's the rho vector for the force RD? Zeros. The force vector is RD X, Y, and Z. And if you take that cross product, you get a zero moment. And next we'll go to the pulley at C. Rho vector for C, since our origin is our about point, the rho vector for C is just 72, 0, 0. And that force vector, we're going to have to think about a little bit. So for this, we know that this force acts in the direction from, what's that point, C, and what's the other point it goes to? I. Okay, so it goes from C to I, okay? But the magnitude of the vector that goes from C to I is something random that doesn't have anything to do with that force, okay? So what we want to do is find a vector that goes from C to I, and then divide it by its length to get a unit vector in that same direction, and then multiply that unit vector by t. So to get that angle, to get the unit vector, in 3 dimensions, I would never think about it in terms of angles. It just, in this case, it's not so horrible, but just get used to doing it based on the points. Okay, so what we're going to do is we're going to, a vector that goes from C to I. So we have this vector U goes from C to I. And to calculate that, we're just going to take I minus C. Our coordinates of I are 0, 44.80. Our coordinates of C are 7200. And so this U vector is equal to negative 72, positive 44.80. And now we want to get a unit vector that's in that direction. So to do that, we just divide all the components by the length. So that unit vector is, anybody have those numbers in front of them? Okay. And so the force vector then is this unit vector times t. So negative 0.849 t, 0.528 t, 0. And then the cross product is 72 times 0.528 t in the z direction in this case. What's that? Okay. Okay. Can someone multiply 72 times 0.528? 36.86? 96. 30.
72 times
0.528. 38.02. Point what? 02. Okay. 01602. I mean, you might have just hit a button wrong. I don't know. Then the next force. So now we're done with this T here at C. The next one is the force from the cable at F. The coordinates of F are 120, 0, negative 10. So that's the row vector. Force for this one the direction of the force we want goes from F to H. So we're just going to calculate that as the coordinates of H minus the coordinates of F. H is 0, 0, negative 100. F is 120, 0, negative 10. So you get negative 120, 0, negative 90. That's in the right direction, but the wrong length. So our unit vector is, you can use the unit v function if your calculator has that on this. And what do you get for a unit vector on that? And so this force is negative 0.8 t, 0, negative 0.6 t, and the cross product of this one, what do you get? So now we've done this force, this force, this force. Now we're at the 140. And that has the row vector of positive 140, 0, 0. That's in inches. The force vector is 140 pounds in the negative y direction, so that's 0, negative 140, 0. And what's that cross product? Okay. Oh, on this one, the second row here, there should be a T on that. And we have one more force. That's that force T2. That acts at the point E, 120, 0, 10. So the row vector is 120, 0, 10. And the force vector is in the direction from E to G. So we're going to get that by just subtracting G minus E. G is 0, 0, 136. E is 120, 0, 10. This is that, what I always call that U vector. So you get negative 120, 0, 126. And so what's a unit vector in that direction? .690, I'll call it 690. What was the second one? Oh, 0. And then the third one? Okay. So this force vector is negative 0.690 T2, 0.724 T2, and what's the cross product? 93 point what? T2, 0. Whew. Okay, so now Newton's second law says that our D vector plus negative 0.849 T, 0.528 T, 0, plus 0, negative 140, 0, plus negative 0.690 T2, 0, 0.724 T2. I hope not. Which one?
Negative 80. Yeah, the 5.
1, 2, 3, 4, 5 forces. 1, 2, 3, 4, 5.
You improve the T for 2 T's.
That's okay. All right. You would have 2 more if you didn't cancel those 2 T's between the 2 pulleys, but all right. So, and all these add up to 0. So that's 3 equations. Yes? Oh, yeah, where did I? Oh, is that what you were saying? 1, 2, okay. That's what you said in the first place. Oh, I missed the negative 0.8. Okay. I agree. Plus negative 0.80 t, 0, negative 0.60 t, and all that's equal to the 0 vector. And then the moment equation. You got 0, then you got 0, 0, 38.02 t. Then you got 0, negative 64 t, 0. Then 0, 0, negative 19,600. Then 0, negative 93.77 T2. Negative 93.77 T2. Okay, so here's our system of equations. How many variables do we have in the equations? 1, 2, 3, 4, 5. Okay, we have 5 variables and 6 equations. Is that a problem? It's not a problem in this case because one of these equations is 0 equals 0. So we have 5 variables, 5 good equations, should work. Unless one of them is in some way that's not immediately obvious, a linear multiple of other ones. And so I'm just going to set up this matrix for reduced row echelon form. It has to have 5 rows and 6 columns. So that's equation 1, 2, 3, 4, 5. And our variables will be RDX, RDY, RDZ, T, T2, and then these are the constants that have to be moved over to the other side of the equation by themselves. So the first equation says RDX we have 1, T's we have negative 0.849, plus some more. So those add up to be negative 1.649 negative. Negative 1.649. And then T2s, we have negative 0.69. And nothing else. The second equation, RDYs, we have 1. T's, we have 0.528. And what? Yeah, so 140 for the constant. And the third one, RDZ, we have 1. T, we have negative 0.6. T2, we have 0.724. And no constant. And then equation 4 is going to be the Y equation for the moments. So T's, we have negative 64. T2s, we have negative 93.77. And no constant. And then 5, T's, we have 38.02. The constant, we have positive 19,600. Everything that's not filled in is 0. And then reduced row echelon form on that matrix gives you the answers. Well, I suppose, could a couple people plug that in? Let's get the answers up here. What? Oh, you're right. It's not newtons, it's pounds. Yeah, so moments would be in inch pounds. These are all forces, so these are all pounds. Yep. All right. So here's first a 2D problem I'd like you to work on together. So let's say we have this rectangular plate. That's connected to the wall by a fixed joint. And the corner is connected to a weight. Say that's 100 kilograms. Let's call that 2 meters. 1 meter. This angle is 45 degrees. And let's say the mass is 50 kilograms. What are the reactions at the fixed joint? Okay, so the answers to this one are that the force at that fixed joint is negative 693.7, negative 203.2 newtons. And the couple at that fixed joint is negative 203.2 Newton meters. Okay, let's do one more. So let's say that we have a pin joint connected to the ground. And it makes a 60-degree angle with the ground. And up at the top, it's leaning against a wall where this angle is 80 degrees. Right. The length of this beam is 0.5 meters. The mass of that beam is 100 kilograms. And then at the center, there's a couple applied clockwise of 1,000 Newton meters. What are the reactions? That's a pin joint down here and a frictionless contact up here. And if you ever see a problem like that and you're not told that it's a frictionless contact, think about the number of variables you have and the number of equations you'll get. This pin joint is an unknown force vector, so that's 2 variables, you know. This, if it's frictionless, gives you 1 more variable. In a planar problem, you only have 3 equations you can use. So if this was a friction contact and you got 2 more variables, you'd have 4 variables, 3 equations. So in other words, the only way you can solve that is if that's a frictionless contact. And so even if you thought there was some friction there, the best you could do is say that that's frictionless, do the calculation, and think of it as an approximation. You know.